technical difficulties. So really glad to be here. And today what I'll try to share with you is our experiences in deploying AI at Stanford Medical Center and what the lessons we've learned, and hopefully some of that will be useful here. So the font and everything is a little bit messed up, going from Apple to Microsoft, Apple to Windows, and from my font to the local font here. So just accept that. It looks pretty on my computer. So the point here is I want to share a little bit of context. I have a dual role. Half of me is a professor doing research with students. Some of you, I would imagine, are PhD students here, where we research ways to bring AI into clinical use safely, ethically, and cost-effectively. I teach a couple of classes. The main one is data science in medicine, which is about 90 students every year. And on the other side in blue is my job with the hospital system, where I lead a team that is focused on bringing things into practice. And as you can all imagine, there's research, you write a paper, and then there's practice, and they don't always neatly line up, as I'm sure you've all experienced. And then below are my disclosures. I've co-founded 2 companies and a nonprofit, Coalition for Health AI. And then the things on the bottom are just my friends. They talk to me all the time, so I might as well list their entities. Okay. So the reason to share this is that I understand the pain of going from publication to deployment. And after I got tenured, I'm spending most of my time trying to bridge these two worlds. So the most useful thing I can share with you is actually non-technical, is about imagining a patient's timeline. And if we just spend the next hour talking about this, mission accomplished. So what we have on screen is an idealized view of a, now let's see if I can understand Korean. Highlighter. Yep, there we go. That's because I know exactly what it is. So we have this time going from left to right, and then things happening to this fictional patient. There's some hospital stays. In this hospital stay, they went to the ICU 2 times. And then here we have all of the different data types that we collect. And now this example only has a few, like ECG, cardiac output, medications, discharge summaries, and so on. But across the medical specialties, Stanford has 123 distinct residency and fellowship programs. Here, I would imagine we have about 26 clinical departments. I would imagine there's somewhere in that range between 25 to 30 unique specialties and then subspecialties beneath them. And then every specialty has 5, 10, maybe 15 things they like doing. So GI people like to put a camera up here or from the rear end and take a video. Radiologists like doing CT scans and MRIs. Surgeons like poking a hole in your stomach and take a little video there. Cardiologists do ultrasounds. They can put a scope up your arteries right into your heart. And so if we imagine all the different specialties, pediatrics, radiation oncology, orthopedics, ENT, and imagine the data that each one of them produce as a track of information, like it keeps going all the way. It's probably 300 tracks of information that we collect. There's genomic information. You could have mRNA expression. You could have proteomics. You could have genetic sequence. You could have whole genome sequence. The list goes on. Everybody has their favorite few modalities. We might have flow cytometry, immunohistochemistry, staining, You might have clinical labs, metabolic profiles. And so if you imagine that rich source of information, so imagine 5 years of time and 300 tracks of information spread across 30 clinical departments, some collected by researchers running clinical trials. And then in the hospital system, under the chief data officer, there's probably 500 IT systems. The things that track the samples going through the conveyor belts, tracking the robots, the blood pressure monitors, the barcode scanners. There's patient data in each and every of those systems, a little bit here and there. There's the EMR, the Darwin system here, that has the majority of it. But pathology slides go to a different system. Radiology goes to a different system. Dermatology pictures go to a different system. Cardiac ultrasound goes to a different system. So if you think of all of that, let's give this thing a name. Let's call it a patient timeline object, not just a view, but imagine it was a data structure. For one person, we have 300 tracks of information scattered over 100, 200 different IT systems. And two things are true of this, always true. If you take any one track of information, just something simple like heart rate, and you go over time, there is nobody that has full 5 years, not even the patient. Some of it might be in the Samsung Medical Center, some of it might be in their primary care, they might go to another facility. And then if you take a point in time and look at all the modalities, there is nobody that has all 300 tracks on one person at the same time. Nobody. Because again, we don't take a biopsy and do an MRI and an EKG every time somebody walks in. We collect what's needed. With me so far? Does it make sense? Are you imagining this thing, 300 rows, 5 years, and if we collected the data, we can put a little one or a little dot over there, and then you imagine this thing, there's very few dots for one person. It's very sparse. And that's what we work with. How many of you here work with genetic information? Clinical information, EHR information, pharmacology, drugs, pathology, anyone? What are the specialties that you are interested in? Radiology? What is the main?
It's very sparse. Mostly clinical.
Mostly clinical. All right. How many internal medicine? Surgery? Very few. OBGYN, pediatrics. Like neonate, again, very different data being collected. You worry about how much oxygen is going to the newborn, because otherwise their retina gets damaged. That's probably collected somewhere. How much oxygen flow is going to the incubator? Probably not in Darwin, probably some other IT system. But if you want to study that, how does the retinopathy of prematurity progresses, you need to track and count that oxygen flow. So the point is that we have all of this rich information scattered all over, and each person is looking at a tiny piece of it. And we'll take this thing, we'll make it flat into a matrix, and then we'll do AI on it. Right? Okay. So I'm going to put AI into this little box here, because that's not what really matters. What matters is, what are we doing to store all of this data? What are we doing to process this data? How fast can we retrieve it? If I told you that for one patient, get all the tracks of information over 5 years, are you going to be able to do it by tomorrow? Or is it going to take you 3 years? And then if you then had to compute with it for, say, 5 million patients of data, it's a 2,000 bed hospital, You go through something like 9,000 outpatient visits a day, 2,000 inpatient surgeries, probably 800, 900 surgeries every day, just given the size. So much data. And if you had to construct this for 1 million patients and then process it, do you have the computational infrastructure to do that? If you had to process whole slide imaging on 1 million people along with their ECGs, how many GPUs do you have in your basement? How much storage? Like Stanford Hospital is small compared to you all. We're 637 beds, let's say 700 beds total. Just our images is 1.6 petabytes. And that's just radiology. You add in pathology, that's like 5 petabytes. Dealing with 5 petabytes is a pain. You know, just transferring it from one server to another takes a while. So those are the things you have to really think about before we get to AI. Okay, let's say we solved all of that. You know, Wanchul and his boss, that's their problem, right? They're going to figure that out. Now you're the researcher. With all that data, in medicine, we do 2 things and 2 things only for a patient. We have to make a decision on whether to treat and how to treat. Those are the only 2 decisions. Now, at any given point in time, you have to make like 10, 15 such decisions simultaneously. And sometimes what you have to do for them conflicts. But at the base, at the core, we're making 2 decisions: whether to treat, how to treat. The whether to treat, from a computational standpoint, is either a diagnosis problem, a classification problem, meaning what the patient has, a prediction problem, what they will have in the future, or a recommendation problem, which requires causal inference to say, what should I do for this patient that will be good for them? Only 3 decisions. I mean, 2 decisions, and the first one has 2 flavors. Now, in general speaking, you know, we say things like building a sepsis predictor. How many of you have heard about a sepsis predictor? There is no such thing as a sepsis predictor. Prediction is about something that has not yet happened. In case of sepsis, what the thing is telling you, what the model is telling you, is that the patient has sepsis and you don't know yet. It's a diagnosis problem. Diagnosis, by definition, is what the patient has. It is a classification problem. There is no prediction happening. But in general language, we say sepsis predictor, but this is not a real prediction. It's like you look at an image and you predict it's a dog. Well, the thing is a dog before you take the picture. And so we have to be careful in how we talk about this, because if you're classifying, you cannot prevent. Only prediction allows you to prevent. Make sense? So language is also really important, because computer scientists will still say sepsis predictor, but I mean, there's no such thing. If somebody sells you a sepsis predictor, I mean, they're either a genius or they don't know the difference between classification and prediction. Which one is a higher probability? So these are the 3 things we do: classify, predict, recommend, or diagnose, prognose, and treat or decide. And we can choose to do these things to advance the scientific understanding of medicine. So that's the first column. Advance the practice of medicine in, say, Samsung Medical Center, or to advance the delivery of medicine at scale, say, across the whole country. The business of medicine, so to speak. And you can use AI for all 3. But you have to be really careful about what you want to do and where you land, because you can't do everything. You have to pick something. So I'll give an example just to illustrate this point, really important. First row, so here, there's this disease called heart failure with preserved ejection fraction. How many people, cardiology related here? How many of you have heard about heart failure writ large? Few? So heart failure, if you ask someone, what does it mean? They say your heart is not pumping enough. That's heart failure. And then you ask them, what is preserved ejection fraction? That means your heart is pumping enough. So this disease, heart failure with preserved ejection fraction, is a contradiction. It makes no sense. But we do assign this label to patients, and researchers study it because it is a contradiction. Like, your heart is fine, but you have symptoms of heart failure. What's going on here? And by using some simple AI, unsupervised classification, which 5 years ago you wouldn't even call AI, it would be called machine learning. There are researchers who found that this disease has 3 subtypes. Subtype 1, you're dead in 2 years. Subtype 3, you're fine for 10 years. So it's a fundamental advance in scientific understanding of the disease. And that's how medicine works. A few years ago, there was only one diabetes. Now it's type 1 and type 2. And there's debate that type 2 might be 3 or 4 distinct subtypes. Now, practice with so this advance has happened. Researchers at Northwestern have done this. They published a paper 3-4 years ago. But practice, going from here to here, advances if 2 more things happen. Patient walks in, and you can do a test. 5 minutes, $1, and you can decide whether the patient has subtype 1, 2, or 3. The test could be a blood test, could be an ultrasound, could be an EKG-based test. Doesn't really matter. Take some input, you apply your AI, and it tells you subtype 1, 2, or 3. You need the test, and you need the treatment. Because if you do the test and classify people into 3 subtypes and still treat all 3 the exact same way, all we've done is waste some time and waste some money. So we need a treatment for subtype 1 who are going to die in 2 years. What are we going to do more for them? And for subtype 3 who are okay for 10 years, can we not treat them? Can we send them home, say, enjoy life? So you need those 2 things to advance practice. Delivery advances, or population level effect, or population health advances, if we do this test and train regime for 5 years, for 5 million people, or 50,000 people, and they live longer, they cost less, they have better quality of life, then we have advanced delivery. Now, AI can help with all 3, but you have to pick which one are you going to do first. So let's look at 2 examples. So here, this is bottom row, middle column. In medicine, there's always this idea that, can I learn from similar patients? For those, how many doctors in the room? Like MD, MBBS? A few. How many PhDs? 1 or 2. What is everybody else doing? I thought those are the only 2 things worth doing. Engineers? What? PhD student. Okay, so that's PhD, graduate student. Yeah. Are any engineers in the room? A few, 2, 3, 4. Okay. Okay. How about statisticians? Nurses? Okay, good. Pretty good mix. Med student. So that's MD eventually. You're not on strike. That's also good. I heard about this strike. So in medicine, I mean, this idea of learning from similar patients is very prevalent. Typically, you rely on the patients you have seen. When you're learning, you rely on the patients your attending doctor has seen, and they're transmitting that wisdom to you. But why not use a computer for that? So the first time a doctor thought of using a computer for looking through similar patients in the US was in 1972, before I was born. And I'm not young. More than 50 years ago, okay? They were already thinking of this. But it didn't work. It didn't work because their patient timeline was short. They only had a few tracks of information, 1 or 2, and they only had 684 patients. And the disease they were trying to make a recommendation for was lung cancer, which in 1972, the prognosis was always bad. So it didn't work. People tried again in the 1980s with cardiac registries, in the early 90s with rheumatoid arthritis registries. In 2015, enough medical data had collected that we at Stanford thought maybe we should do this again and see if we can run a bedside service. Just like there's radiology and pathology and so on, like you can do a biopsy on the liver and look at it under a microscope. Can I take this patient and use that to find everything similar from the database and produce a report under a day, turnaround time, in describing what happened to similar patients? So there's medicine involved, there's computer science involved, there's statistics involved because you better do your causal inference right. And so we did this for about a year and a half, did 100 cases, and wrote this New England Journal Catalyst paper of using aggregate patient data at the bedside by an on-demand consultation service. So I'm going to show you the results for that. Here, the colors again don't show up. That we can blame Microsoft and Apple for that. So on the x-axis, the number of unique doctors. The y-axis is the number of unique questions. Internal medicine was the largest. That circle, if it showed, would be about this big. Oncology was about here. Cardiology about this size. Derm is here, and so on. Of the 100 cases, we did at least one from every specialty, every clinical specialty. Pediatrics is right here. I don't think we had neonatology separate, so subspecialty in pediatrics at our location. Out of the 100 questions, 17 times we said we can't answer the question. That's really important. Your AI needs to know when to not speak. Because if there's not enough data, if there's not enough certainty, you're better off not saying anything instead of giving a garbage answer. The 83 that we did respond, 10 of them changed patient care. 10 divided by 83 is about 13%, which is the rate at which a typical second opinion would change care. We're an academic facility, so 52 of those people did further research. They basically wrote an intro and a discussion and submitted to a conference and got it accepted. Some people even got JAMA papers doing this. And then 17, the analysis was okay, but not super conclusive. So they had to do follow-up analysis to get to the answer that was necessary. So why does this matter? On the left is a study that I was not involved with, where a few physicians tracked how many questions or how many decisions they make at the bedside for about a week. 80% of them had no basis in any prior published data. Less than 3% had a study specific to the question at hand. And this you can back up with many different ways. Even if you take something really well studied like cardiology, only about 20% of their guidelines have level A evidence, which is based on randomized controlled trials. And you ask a cardiologist, how often is it the case patient walks in and they're a perfect match with a guideline? Maybe 10% of the time, 20% of the time. So if 20% of your guidelines are RCT based and they're applicable 20% of the time, multiply the two, 4% of the time you have evidence. And these guys also found about 3%. By and large, 5% is when you really have something that applies to the patient right in front of you. Every other time, we're taking our educated guess. That's why deciding without data. We store it in the EHR system, and we never go back. Here, you probably, the Darwin system is probably 15, 20 years of data, longitudinal. Amazing resource. So on campus, when this project finished, our dean and CEO basically said, so Nigam, how are we going to scale this and keep it going? And I said, well, I have my 3 students and you can support the lab forever and we'll keep doing it. And they said, no, we're talking about supporting it nationally. I was like, oh, that's a problem. And so we spun out this company because, that's what you do in Silicon Valley. And the company now does all of this. I don't have to do these reports anymore. And there's very high usage at Stanford. On the left is just one department. I happen to pick it because that's the last group I presented with, and I collected the information. OHNS stands for otolaryngology, head and neck surgery, so ENT at most other places. They've done about 152 analyses. We spun out the company in 2020. It started offering service in late 2021, so it's about 3 years. So they've probably done 50 every year. It's one a week. They've got 30 publications. And then over the whole hospital, about 383 doctors use it actively. And a doctor who uses the report once uses it about 6 more times. 85%, 84% of it is for research, and then the other 15% is for patient care, 4% is direct, and then 11% is about groups of patients, so for quality improvement. GI is another specialty that's very active. They did a bunch of these reports, and then at one of their main conferences, they got a whole session just for themselves. I don't know, it's kind of funny then if you have one institution having all the sessions, all the talks in one session, like nobody else goes, but you know, they pulled that off once. All right, so that's that. We just took a tour here. Now let's look at one other piece, making predictions. Making predictions is the easy part. Doing something about them is hard. So you have to think about predict and act. So what I'm showing you is we had 2 models. I'm only going to talk about one. I'll talk about the advanced care planning. Advanced care planning is this conversation with someone who is near end of life to say, what is the way in which you want your care to be done when you're in the last stages? It's a very difficult conversation to have. And it's unclear when to have it. And there is incontrovertible evidence from RCTs that patients who get advanced care planning, they live longer, they cost less, and they have a better quality of life. But the US absolutely sucks at doing advanced care planning because we love doing procedures. The median time at which somebody says, all right, let's talk about this is like 2 weeks before somebody dies. I mean, at that, it's too late. It's too late. So we wanted to move that earlier. So we built a model, and we built a model to predict who's going to die in 1 year. That was the easy part. It took us 3 months to build the model and test it, validate it, no problem. And that happened in like 2017 or something. But it took us 5 years after that to design the appropriate response. Model shows a probability. Who's going to do something? What will they do? How will we track it? And when we started the project, the palliative care department that does advanced care planning, they say, oh, we can only do 4 or 5 a day. I was like, guys, if you can only do 4 or 5 a day, why are we making a prediction? Because if I tell you these are 8 more patients, you're still not going to see them. And so they started creating a program where we taught medical students, nurses, respiratory therapists, physical therapists, spiritual care workers, anybody who has the time can have this conversation with the patient. You don't need medical expertise for that. Actually, the less medical expertise you have, better off you are in this. And so after we were done with all of that, the plot that I wanted to show you is this end part starting from 2022 to later, is that the number of total advanced care planning is going up and the ones done by the physician is flat or going down. Meaning other people have now taken up that work. That is when you can believe that, okay, your model now has impact. And so in prediction, I mean, you might have fall predictions, you might have readmission predictions, you might have predictions about how many phlebotomies you're going to need to do today. But that prediction is not useful until you can send nurses from other floors to the phlebotomy lab, because otherwise patients are still going to wait. So predictions that do not change actions, useless. Start with the action and then figure out what the prediction has to be. So here, The point here is that what can you achieve given your work capacity? So a lot of times AI conversations happen about the model, because that's fancy. Deep neural networks and CNNs, and you can use all sorts of words that doctors don't understand. It makes you feel good, right? Because usually it's the doctors using weird words that you don't understand, all the Greek and Latin. But what matters is paying attention to these two parts. That what is your work capacity? And policy, not like government policy, like at your institution, what number do you need to see in that predictive model at which you'll stand up and do something? In case of that advanced care planning, is it 5% probability of death, 20%, 80%, 95%? What's your threshold? And so there's about 25 papers worth of research that we've done studying this interplay. And in the end, it boils down to this one plot, where after you've made the predictions, you rank order them, 1 minus the probability. So it starts at 0 and goes to 100. And then as you take follow-up action on one case, you get some benefit. Time saving, quality of life, money, something. You get some benefit. And as you take action on the second one, you get more benefit. And then you get more, and then you get more, and keeps going for a while. And then you start seeing diminishing returns. The most important question is, how far down the list can you go? What is feasible given your work capacity? Because without that, no patients benefit. It's just a mathematical exercise. So our framework for all of this, we call it a firm analysis for evaluating fair, useful, reliable models. And that's on the next slide. Yep, there it is. So before we write code, before we do any deployment, we ask this question: given a prediction, what action would someone take? If they can't answer this, project stops right there. Don't waste time. If that is clear, then we look at the cost of the action, we look at the work capacity, what is the net benefit we can realize, the plot that I just showed you in the previous slide. And then in the back, we also do financial projections. Can we sustain this? Or is the CFO and CEO going to get upset? We look at ethical considerations, because often we've found situations where doctors are convinced this is the right thing to do, and you go talk to the patient, like, hell no, we don't want that. So all of that happens first, and in the first stage, before anything gets deployed. For about 10 of these assessments we do, maybe 1 or 2 pass to the second stage. Sometimes even less. At the second stage, that's when we talk about, what's the model, how are we going to train it, what's the deployment, and all of those things. And then once it's deployed, so you have to monitor to make sure it's working. And you also have to monitor to make sure it's doing what you expected it to do. Because if no actions are being taken, why are we wasting time? You should shut it off. And so that's impact assessment and honest evaluation. That is it doing what we said it would? Like in that case, advanced care planning. Our hope was that the rate of advanced care planning would go up without burden on the doctors. First, rate went up with burden on the doctors. We went from having less than a 1% advanced care planning to almost 14%. But then the project is truly successful when the burden on the physicians also goes down. All right. Now, all of this has to be embedded in governance. This is responsible AI lifecycle. It's a little bit cut off there. This is just a fancy flow chart that how we do it at Stanford. But the point here is that there are these 4 groups, 1, 2, 3, and 4, and I'll walk you through them. So the group 1 is the people at the front lines, the operations. They are the ones who have a problem that needs to be fixed. Typically, it comes to IT, and then that's where we define the use case and say, who's going to do what? Prediction happened. If there was a magical predictor, what is the action you're going to take? If there's adequate details, so we have enough details, we send it for this assessment, this form assessment. After that, we can ignore this G10 thing. This is the main committee. Our CEO is on the committee. Our dean is on the committee. They meet every month, look at these reports, and they have to decide, are we going to do this or not going to do it? Even the chief financial officer is on the committee, because if we do it, they have to sign off. And if we don't do it, they have to tell no to the requester. Not the data people, not the AI people. It comes from the boss. Because otherwise, they'll always try to go around you. For things we do, you can ignore the app team, DS team. That's just our internal team structure. You also have to create a monitoring plan. The things that we talked about on the previous slide, this stuff, monitoring and prospective evaluation, so you know whether it's working. That's sort of the crux of this. Now, at other organizations, of course, this flowchart will look different based on your anatomy, but these are the four constituents. You have your frontline people, you have your IT staff, you have your machine learning and data science people, and you have your governance. And these four groups have to figure out what is their dance, and who decides. All right, so all of this is done by a team on our campus. We call it the data science team. We don't call it the AI team. Because, I mean, AI is today's hype. Tomorrow it could be something else, who knows? Maybe AI goes bad and machine learning comes back again. Maybe sideways learning happens. I don't know what will happen. But data science is not going away. The use of data, that patient timeline, some computation on it to make a decision. Those three things not going away. So we talked about this interplay between the model capacity and so on. We talked about the firm assessment. The other two things that this team does is this infrastructure and processes. So I showed you the process, the responsible AI lifecycle. That was this thing. And then infrastructure is the computers and the disks and the data lakes and all of that, so that you can actually do what you're going to be asked to do. And then last but not least is do 3 to 5 projects that have some enterprise value to the larger organization. Can't just do science projects all day long. So that's the team. And we had all of this figured out by 2022. I started my job in March of 2022. All of the research had already done prior to that. We set everything up. We have these nice little pictures and everything and diagrams, and then LLMs come around in November 2022. I was like, oh my goodness, what are we going to do now? But I'm really a believer in that timeline. So let's go back to the timeline. I put language in quotes because when people talk about language, usually the meaning is natural language, like English, Korean, Spanish, or what have you. But the timeline has a language from a computer science standpoint. So from a computer standpoint, a language is a sequence of symbols or sequence of tokens, if you will, from a finite vocabulary. So sequence of protein, a sequence of amino acid, language. Sequence of nucleic acid, language. Sequence of words, language. Sequence of medical events is a language. You get diabetes diagnosis, you see HbA1c testing, you see blood testing, you see metformin, you see insulin, you see retinopathy, neuropathy, kidney failure, death. Over multiple years, but it's a language. It has huge gaps in between. Just because you got diagnosed with diabetes at 40 doesn't mean you're going to die tomorrow, usually another 40 years. So if we look at and you guys have 20 years of data on patients. So if you look at this language, there's nothing to read. There's no symbols there, just tokens like ICD codes. I don't know, do you use ICD in Korea? ICD 9, 10, 11? Okay. Lab tests, LOINC, SNOMED codes, mean, there's always a coding system, and the number of codes is fixed. And you pick from there so that insurance will honor it. That's also true in every country. So you can use this EHR language, and then we can do these models in two ways. The part in the top is the usual language where you're feeding documents, and you train a model and it does chat and summarization with you. But you can also train these models on timelines, tokens of medical events. In fact, there's something called a medical event data standard that Edward Choi, who some of you know, is quite actively involved with. So now you have these events over time. You train a language model, and I say language, but it's really best thought of as a sequence model, because it doesn't talk to you. It's not going to write you a poem or anything. But it can forecast what's going to happen. It can tell you what is the next token that is going to come. And it can even tell you by when. Because in natural language, we don't train that way. We don't train with the goal of predicting how many words will pass till I see the word Samsung. We don't do that. We just predict the next word. But in medicine, what we care about is how many years will pass till heart attack. So you can train the model that way. So you change the pre-training objective of the model. So I'm going to spend some time in both the blue and the red zone. How am I doing on time? 10 minutes? 5 minutes? Okay. The first one is about using things that others have built and using them in medicine. So we said, all right, what is everybody doing? So we did a review of about 519 publications and asked 5 questions. We asked, what is the data by which they're evaluating a language model like GPT-4 or Llama or whatever? What is the healthcare task that is being done? What is the language task being done? And what is the metric for evaluation? And the 5th question was, what medical specialty? So 95% of the papers were published doing experiments without any EHR data. I was like, really? So yeah, only 5% were based on EHR. It's like, okay. For the healthcare task, the top task you see here, we gave it a benign name called enhancing medical knowledge. It's basically asking and answering multiple choice questions. Language task, again, question answering, no surprise. These are all models doing USMLE exams. We love accuracy as a metric, and factuality, nobody pays much attention. Calibration and uncertainty, nobody pays much attention. Like for a statistician, if you can't calibrate and you can't tell me what uncertainty is, like, do I really believe anything there? And then most of the work was coming from internal medicine. Okay, so that's just baseline. What is everybody doing? So we said, all right, but what do we want to use this for? Well, there's a bunch of people who are using it for medical diagnoses, making treatment recommendations, care coordination and planning, triaging patients. So we said, let's test it. So on the left is, remember I showed you that bedside consultation service, which we had 100 questions? We gave those 100 questions to GPT 3.5, that's the left pillar, and GPT-4, right pillar, and said, answer the question. And we had a reference answer. You can see that agreement is going up from GPT 3.5 to 4. Disagreement is going down. Unable to assess is going up. So we showed the answer to 12 doctors and asked them, is the answer agreeing with what we know, not agreeing, or you can't tell? But the main result is that about half the time, the 12 physicians cannot agree what is the case. So passing exams doesn't mean this thing can give you some value at the bedside. Then we said, okay, let's do some simple language tasks, like summarize from the EHR the stroke the patient had and their neurological deficit. That's a command, a prompt I want to give to the language model. We give the EHR. So the language model gets the EHR and this prompt. It writes out this thing in the green box. And we have a doctor writing out the yellow box. And then we compare. 35% error rate. 35%. So we said, okay, now we need to do this a little bit more systematically. And we started creating a large benchmarking data set with multiple tasks in 5 categories, like diagnostic decisions, planning treatments, documenting reports, patient-provider messaging, and so on. And then for everything, we created a data set where we have a medical record, a real medical record, because otherwise, I don't believe it, a prompt, a true answer, and a rule by which I can decide whether the language model's answer is matching the true answer or not. So that's the evaluation metric. And we just benchmarked 6 models. Now, there's some very interesting things. Look at Llama 70B instruct. It's pretty good as GPT-4. And it's free. You can comply with Korean law. Data are not going to go to the US. You can run it locally. Gemini from Google looks really bad, but it's not really bad because most categories, it says it's a medical question I will not answer. But when it answers, it's the best. So that's also good to know. You can create your own data sets and do such benchmarking. The framework is open source. All right, so last we'll touch on the red part, which is the timeline models, these ones. So here we're making forecasts of what's going to happen. And the solid blue is this timeline train model. Ours is called MOTOR, or multiple outcomes time-oriented representations. And what we're looking at is the ability to train classifiers for 15 labels. And on the x-axis is the number of examples we have, positive examples. Y-axis is accuracy. And the key point is this one, that if I'm using this timeline trained model with 128 examples, I can train a classifier better than what you can train with all the data using standard techniques like regression and gradient boosted model. This is huge. You can now train classifiers for rare outcomes. So we're using this technology to build classifiers for undiagnosed rare diseases. But in an operational setting, you can still train for things that are low prevalence. And it's, you get some higher accuracy, you need 95% less training data, and it trains 8 times faster. All right, so I'll basically wrap up with, I think this is my last slide, that as you think about language models, focus on verifying benefits and focus on how do we deploy in a way that doesn't give more money to the tech companies, but does have some benefit to our patients. All right, so this is all the people, the bedside consult, we used to call it green button. These are the 4 people who did the work. Ken Jung actually is from South Korea. He was born here, now he's Canadian. And this is the data science team. There's a bunch of people, it's about 40, 50 people. Couldn't fit them into a picture. And then this is my research group, which does most of the paper writing and so on. And I'll stop here. All right.